introducing some things that are actually in our textbook at this point. Wrapping functions were not in our textbook. So we're officially in, I guess you could call it chapter 7. If you want to follow along in our book, that's on page 257. Talking about things like arc length. It's the length of an arc, which is some terminology we've used already. And area of a sector area, which we will define here shortly if you do not recall from geometry. So those are our two key topics for today. Again, it's in chapter 7. You can find a lot of terminology that we've talked about before, including things like revolution and period and initial position and quadrantal angle, radian measure, degrees, and coterminal angles and reference angles and different things of that nature, including some examples on conversions from radians to degrees and vice versa. So we're going to begin today and talk about arc length. And if you recall from a previous video, radians versus degrees, I mentioned how if you could remember the definition of a radian and the fact that one radian occurs when the arc length is equal to the radius of a circle, that a lot of things would become a lot easier for us here in math. So we're going to look at this arc length concept here first. Now arc length is nothing more than if I take a circle, and I'm just going to look at part of a circle here, and let's say I want to look at the measure of this arc right here, which is formed by the initial ray here in standard position, right, the positive x-axis, rotated up some unknown angle, we'll call it theta, till we get to the terminal ray, which is this guy right here. Okay, so the length of the arc right there, typically represented by letter S, arc length. Well, if you think about it, the arc length is simply a piece of the circumference. Okay, arc length is a fraction, right, a fraction of the circumference. And this is where the understanding and different things, like you guys know formulas from geometry. You know that circumference is 2 pi r. Circumference of any circle is defined by 2 pi r. So half of the circle would be half of 2 pi r. A quarter of a circle would be 1/4 of 2 pi r. Well, we say a half of a circle because we have 180 degrees out of 360. A quarter of a circle is 90 degrees out of 360. Well, I don't know how many degrees I have, but you know what I do know? I have theta degrees out of 360. I have this fraction right here. I have part of the entire circle. Part of entire circumference. I'm not sure what that spelled, but it's supposed to say circumference. I have part of, right, some fraction, theta out of 360, of the entire circumference. That is my arc length. Notice the notation right there. That is my arc length in degrees. Okay, this is my degrees formula. Kind of ugly. Theta over 360 times 2 pi r. Well, what's it look like in radians? Radians, remember, is 1 radian, remember, occurs when the arc length is equal to the radius. So we showed in a previous video that every circle has an arc length. Well, every unit circle has an arc length of 2 pi. In fact, every circle has an arc length of 2 pi radians because you have 6.28, 2 pi, 6.28 radii going around the edge of the circle. And I showed that breaking up into pieces in the radians versus degrees video. If you need to take another look at that, feel free. Okay, so if I'm talking about the arc length, which I should put an S here. I started out doing circumference and 2 pi r. If I'm talking about arc length, S, and let me change this guy here to an S as well. All right, if we're talking about the arc length, I again have a fraction of the entire circle. Well, the slight difference is we know an entire circle is 360 degrees, or it's 2 pi radians. Well, guess what? I have theta in radians. I have 2 pi in radians, right? This theta was in degrees, remember? This is in radians. which we typically don't write this stuff. I'm just kind of doing it to show. Radians, radians. So units crossed out, just like degrees crossed out here, and I get a distance. Well, besides the units crossing out here, 2 pi and 2 pi crossed out, and I have this very easy formula. Arc length is theta times the radius. The angle in radians times the radius. And I still have the same idea. I have part of the entire circle. And that's it. Arc length is a fraction of the circumference. Fraction of the circumference. All you need to remember is that you have some unknown angle out of 360 or some unknown angle out of 2 pi, depending whether you're in radian measure or degree measure. All right, we'll do some examples here briefly. Now let's go to sector area. Well, sector area is very similar, but now we're not talking about a part of the circumference. We're talking about a part of the area. So if I draw this slice of the pie, if you will, this sector, and let's shade this guy in here, we're now talking about this, right? The entire pizza, not the crust, right? The crust was the sector, or the crust was the arc length. The piece of pizza itself is the sector. I think I shaded most of it there. Pardon me, we have a phone call coming in here. Let me pause this up for us. Sorry about that. Just some annoying telemarketers there, I believe. So where were we? We were talking about sector area. That was the second phone call I've gotten in the last 5 minutes here, maybe 10 minutes. Quite annoying. Okay, so we have some portion of the circle, right? The rest of the circle continues around here, right? And we have a fraction now, not of the circumference, but a fraction of the area. So again, more comfortable, most of you, degrees. I have, for my area of the sector, which you know what, oddly enough is denoted by the capital letter K, typically area is pi r squared. Well, now if I'm doing area of a sector, I have a fraction of the circle times pi r squared. Pretty ugly, but same deal. I have part of the entire area. Now let's switch gears. Let's think radians. Radians tells us I now have, still I have a fraction, but my fraction is some angle out of 2 pi times pi r squared. Pi's cross out, and I'm left with 1/2, right, over 2, theta r squared. Pretty nice formula considering the alternative. So if you can make quick transitions from degrees to radians and recognize 60 degrees is pi over 3, and 30 degrees is pi over 6, and 45 degrees is pi over 4, and 120 degrees is 2 pi over 3. All right, you're going to be making some very simple equations for yourself when you're dealing with sector area or arc length on the previous page. Let's look at a couple examples here. Find the arc length and sector area of a piece of a circle of let's say 30 degrees of a radius 7 circle. So what I'm looking at here is I have 30 degrees and my radius is 7. All right, well, my arc length, right, this piece out here, my arc length is, I'm going to look at 30 degrees. You know, I don't like that. I like pi over 6 better. I have a fraction, pi over 6, out of the entire circle, and the entire circle is 2 pi r. 2 pi's cross out. My r value is 7, so I have 7 pi over 6, and whatever the units are, centimeters, meters, yards, feet, whatever. Radius 7 whatevers. My arc length, or sorry, my area of the sector here, that phone call is still bugging me. The area of the sector, I still have pi over 6, right? 30 degrees out of 2 pi times pi r squared. I'll put the r in this time. 7 squared. Pi's cross out. Pi over 6 divided by 2 is pi over 12. Or you can think of it this way, 1/2 pi over 6 times 7 squared, which is 49. So I have 49 pi over 12 units squared. So there are our two answers. Piece of cake. Okay, I hope you enjoyed learning about area sectors and some arc length when talking about radians. Have a nice one.